Hello, what we're going to work on today is more stuff with graphing functions, but this time using parent functions and translations in order to do so, rather than just using a table of values. And we're also going to talk about some more stuff with domain and range based on what we're looking at, and some mathy stuff. So we'll do so using these four functions. What we're going to do is sketch the graphs of them, but we're going to refer back to the video that I had posted about guaranteed pass notes, or what I had called the graphs of algebra. So we're going to use that as the background, because those actually represent what's called parent functions. So we're going to dive into parent functions and translations, and then use that to graph each of these, and then talk about the graph's domain and range. So a brief rundown real quick of parent functions. And this goes back to, again, that video that I had made called the graphs of algebra, or what I've called the guaranteed pass notes. Because if you understand those, you're guaranteed to pass. So basically the guaranteed pass notes had a function that looked like this: y equals x, or if you remember, f of x equals x. And the graph of an equation that looks like that is a straight line. And so any straight line from function notation, any graph is going to have that. Then we had a absolute value function, or we could call that also the f of x is equal to the absolute value of x. And if you recall from that set of notes, that was basically a V shape. And we also had y equals x squared, or again, f of x equals x squared. And we compared that to the absolute value graph, where the absolute value graph made a V. The y equals x squared makes a parabola, or a u, what we call a quadratic function. And so that made a u. And then lastly, for our purposes for now, we had y equals the square root of x, or again, f of x equals the square root of x. And the shape of that graph looked like basically an a parabola knocked over on its side, but then only the top half. Because if you remember, we talked about parent functions, or domain restrictions, and this being a function. So we have to remember what those parent functions look like. Now with that, what we have to look into is, given a parent function, how do these graphs shift based on equations, how they're written? So I'm going to get into a little bit of that. So in general, if we have a parent function, let's call it, y equals x, or f of x equals x, there's going to be some interesting things that occur with it. What this looks like right now, by the way, if I were to expand how this function looks, it could look like this. Y equals, this is going to be kind of weird, 1 times x minus 0 plus 0. That's what that looks like. Okay, so what this is, if I use better colors. So if I have 1 times x minus 0 plus 0, what this means is it gives us that. I mean, there's all these invisible things that are happening to it. We just can't see it. And the same thing with actually all of these. I'll pick another one. For example, y equals x squared. There's stuff happening to it, we just don't see it. Okay, so there's things happening to this graph, we just don't see it. Okay, so this is y equals, 1 times x minus 0. So there's x minus 0, but this time that x minus 0 is being squared, and then we're adding to that another 0. Okay, so all these invisible things are happening to it, we just don't see it, right? So there's the invisible things that are happening to it, we just don't see it, and it ends up with this. Okay, so we have this crazy looking thing is the same thing as this, and its graph does that. So it's a parent function. All these invisible things are happening to it, we just don't see it. So now what we do is kind of expand this invisibility thing, because what happens if we start seeing things? What happens if we start seeing these numbers now, and then how would that affect the graph? So the way a normal translation works is that you have a bunch of invisible things, or not so invisible. We could have an A, which is a normal variable that impacts what's called stretching and compressing. We have an X minus an H, and then a plus K. And so all of these things come together to impact the graph. So, and all of these things move the parent function in one way or another. And so we're going to talk about how that works. So if we look at this example, and we have our parent function there, what does that number on the outside do? So this A, this number on the outside, what does it do? It either stretches or compresses a graph. In the sake of a linear function, it is the slope. It affects the slope. So it stretches, it compresses a graph, and it also determines whether or not the graph goes basically up or down. Up or down, or reflecting over the x-axis. So I'll just call it up or down, or reflection over the x-axis. So if it's positive, it's negative. And again, I showed this in the previous graphs of algebra notes. So that's what A does. A deals with stretching, compressing, slope. It can open, it can narrow, and whether or not it opens up or down. Now what does the H do? Now the H shifts the graph left to right. Okay, so it either shifts left or shifts right. Now this is interesting, because since what's happening is we have X minus H, right? So if you read X minus 3, it would be shifting to the right, okay? This is what's interesting. So it shifts left if it reads X minus H. It shifts right if it reads, shifts right X minus H. It shifts left if it reads X plus H. And you'll see how I'll demonstrate that in a second. And then lastly, we have the plus K. So the plus K will shift a graph up or down. Shifts up if it's plus K, shifts down if it's minus K. And we'll be able to see that in a couple of examples. And I'll make one real quick one. So let's do a fast example, and then we'll jump into those four things. So let's say we had y equals x minus 2 to the second power. Okay, so what this means is that we take the parent function. Okay, remember the parent function is y equals x squared. And we know that y equals x squared has a graph that makes a parabola. Okay, and that's on the xy axis, makes a parabola. Well, how will this affect it? And so let's look. Now my argument for x minus h is that if you read x minus 2, I'm arguing that it's going to shift to the right 2. Okay, that's my argument. You say if there's going to be a vertical shift, or excuse me, a horizontal shift, which way will it go? And you might think that x minus 2 is going to shift to the left, right? Well, let's take a look. So we know it's going to be shifting left or right. Is it going to shift left or right? We don't know. So let's make an xy table and see what's going to happen. Okay, then I'll do this really fast. And again, my argument is that this is going to shift to the right. And of course you're thinking, that's impossible, because it says minus 2. It should be shifting to the left. So let's find out. So let's say I make x, let's say 0, 1, 2, 3, and even 4. Trust me, those are good numbers. So if I make x 0, and I plug x in for 0, I get 0 minus 2 squared. Negative 2 squared is 4, positive 4. So we're going to get positive 4. If I plug in 1, 1 minus 2 is 1, 1. All right, so positive 1. 2 minus 2 is 0. Okay, and then 3 minus 2 is 1. That's going to be 1. And 4 minus 2 is 2. That's going to be 4. Okay, and that's going to be our ordered pairs. Okay, so I plug those ordered pairs in, and we're going to graph those. Like I said, trust me. I just want to demonstrate what's going to happen. Remember I said I think this is going to shift 2 units to the right. You're saying, no way, that's a minus, it's going to go left. Well, let's prove that. So we have our ordered pair at 0, 4. So we have 0, 1, 2, 3, 4. We have an ordered pair at 1, 1, an ordered pair at 2, 0, ordered pair at 3, 1, ordered pair at 4, 4. Well, look what's happening. What we did is shifted our parent function 2 units to the right. Holy cow. So this is 2 units to the right. That's amazing. It says minus 2. It's going to the right. And you know what? I agree. It looks confusing, but there it is. There's the proof. Proof is in the pudding. So that's why we have to pay attention when we have in the grouping symbol x minus h shifts to the right, x plus h shifts to the left. Okay, so this note becomes really, really important to remember. Now the k, shift up, shift down, that's perfect, straight on right there. Okay, so remember what a does. Stretch, compress, is it up or down? What h does, if it's minus h, it's to the right. If it's plus h, it's to the left. And then what k does. If it's plus k, it's up. If it's minus k, it's down. Those are the notes. The rest is practice. So let's practice, right? We're going to take a look at these equations, and then we're going to graph them using the parent function, and then start talking about domain and range. So we look at number 1, and we have to remember, well, number 1, we've got this crazy looking thing. There's a square root of x, and it says plus 4. Now we got to remember, what is the parent function? Okay, so the parent function is y equals the square root of x. And if you recall, the graph of y equals the square root of x starts at the origin and just does that little bloop thing, right? Like that. That's the parent function. And what we're going to do is use that parent function and look at the equation and figure out what's happening. So we look at translations, right? How does this work? Well, with translations, we would have, in this case, we would have a times x minus h plus k, right? And you know, a would deal with making it smaller or making it steeper, or if it's up or down. Okay, that's what a would affect. Is it a narrow line? Is it a big dip, or is it up or down? What h would affect is the horizontal shift. If it's minus, it's to the right. If it's plus, it's to the left. And then k would mean that it's shifting up or down. So all these impacts of what's happening. And now we see, when we look at the original equation, the only thing that we see, we don't see an a, we don't see an h, but we do see a k. So what this means is that this particular parent function is going to move up or down. It's actually going to move up 4 units. So we have our original graph, rough sketch, and now what I'm going to do is draw another graph and take a look at the parent function and then just translate it. Okay, so remember, the parent function is this one here, basically the one in red, right? Well, it's actually 1, 1. I mean, it looks like that. That's your parent function. Now what is it going to do? We have that plus 4. So we're going to take everything and shift it up 4 units. So what's going to happen is that this was the original starting point for the parent function. Well, the new starting point is going to be up 4 units. So up 1, 2, 3, 4. We're at a point at 1, 1, so that's going to go up 4 units. Every single point of the graph is going to basically shift up 4 units. So all this is happening is taking the parent function and it's shifting up 4 units. And so when I say in the instructions to describe the translations, that's all we're saying is basically take y equals the square root of x and then shift it up 4 units. And that's how you would describe the translation. right? We're taking the parent function, shifting it up 4 units. There it is. Now what we need to do is think about domain and range. Okay, we look at the graph, and now we're thinking about domain. How far to the right, how far to the left? Okay, so we go back to domain and range. And if you look at the graph, the domain starts at 0 and goes all the way out there. All the way out there. All the way out to the right. So the domain starts at 0 and will continue on to infinity. And if you remember how we call that, we use interval notation. And the domain goes from 0 to infinity. Now what about the range? How low, how high? Well, how low does this graph go? It only goes as low as 4. 4 is as low as it goes. And it's going to continue going high. So it goes from 4 to positive infinity. If you remember, that's the range, how high, how low. It's going to go from 4 to positive infinity. And so that is the domain and range. And now we're going to see, does that make sense? Okay. So remember I asked for the domain and range. Domain goes from 0 to infinity, and the range from 4 to infinity. Does that make any sense? Well, look at the equation. Can we take the square root of a negative number? Not in the real world, no. So in order for this equation to make sense, x is going to have to be 0 or higher, because you can have the square root of 0. So the only thing that x can be is 0 or higher. Take a look at the graph. X can be 0 or higher. Take a look at the graph. X could be 0 or bigger. And what about the range? Since this number, once we take the square root of a number, is going to be positive, and the lowest possible domain is 0, then the lowest possible range is 0 plus 4. Everything else is going to be higher. So the range is going to start at 0, go all the way to, the range is going to start at 4 and go all the way to infinity. And if that doesn't make any sense, well, look at the graph. How low, how high? So you can see that everything makes sense based off the equation itself. So we've described the translation. We have graphed the new equation, We have stated the domain and stated the range. We stated the domain and range. And that's what we're going to do for all of these. Okay, now I'm going to start moving a little bit quicker. So let's look at number 2. For number 2, we have g of x is equal to negative absolute value of x minus 5. And so what does this mean? This means we have to pay attention to our parent function. So remember, what is the parent function? The parent function is y equals the absolute value of x. Right? We know the parent function is a v. So we just take a rough sketch. What would that parent function look like? It looks like a v. And that we know from guaranteed pass notes. Well, what's going to happen if we have translations involved? So if we have translations involved, remember what A does. A stretches, A compresses. Okay, so what does A do? It can make it really thin, it can make it really wide, or it can turn it upside down. That's what A can do. It can make it really thin, make it really wide, stretch or compress, or invert it, flip it, actually reflect it over the x-axis. The H then has the impact of horizontal shift. Remember, if it's minus H, it's to the right, and then plus H is to the left, and then K is the horizontal shift, right? Or excuse me, vertical shift. So plus K up minus K down. Now we look at the original equation. The original equation has, first of all, the minus out there. So we can already tell this thing is going to be reflected over the x-axis. It's going to open down. Okay, so this graph is going to open down, reflecting over the x-axis. This has x minus 5. And as I demonstrated that trick with horizontal translations, that means it's going to go to the right 5. So we can already say that we're going to take y equals the absolute value of x. We're going to reflect it over the x-axis or have it open down. I'm cool with you saying open down, although reflecting over the x-axis is better. And it's going to shift to the right Okay, it's going to shift to the right 5 units. Because it says x minus 5, it's going to shift to the right 5 units. So we can graph it super duper easy. Okay, so we can take our coordinate plane, and we know what the parent function is going to look like. And if you remember, the parent function again was that v, right? That was the parent function. That was y equals absolute value of x. And what we're going to do now is reflect it over the x-axis and then shift it right 5 units. So that means where the point at the original was here, now it's going to shift to the right 5 units. 1, 2, 3, 4, 5. And instead of opening up this way, it's going to be a v down this way. How cool is that? That is actually our graph. This is the graph of f of x equals negative absolute value of x minus 5. So we have the skill now of graphing with using translations. Now what we need to do is figure out the domain and figure out the range. So now the domain is how far will it go from right to left. And as you can see, it's going to continue going forever from right to left. So clearly the domain is from negative infinity to positive infinity. That's our domain. It's going to keep on going forever to the left, forever to the right, from negative infinity to positive infinity. What about the range? How high, how low? It's not going to have it. It's going to go as low as possible. It's only going to go as high as 0. That's as high as that range is going to go. And so we know the range is going to go all the way from negative infinity up to 0. Okay, so remember, we keep everything in order. So the range is, this graph is only going to go as high as that. Okay, so the domain goes on forever. The range only goes as high as 0. We'll never go beyond 0. And that makes sense when you look at the equation. And when you look at the equation, you have negative absolute value. The absolute value will always be positive, but then the negative makes it always negative. So the range makes sense. And there is no limit on what x can be, so the domain makes sense. All this stuff makes sense. All right, so now what we can do is take all that and apply it to funkier stuff even. All right, so even funkier stuff. So let's take a look at the graphic number 3. All right, so number 3, we have h of x is equal to another square root function, but let's see how all of this translations take place. We know the parent function, of course, is going to be y equals the square root of x, and we know that the parent function will look something like this. Bloop. And that's our parent function. Now what we're going to do is use translations to mess things up. Okay, so remember how translations work for square root. Okay, it's the same as anything else. A determines up or down. H determines right or left. K determines vertical or vertical shift. Okay, so A would determine this or this. I should probably use blue. Bloop. Does it graph look like that, or does it graph look like that? K would H would determine horizontal shift, and K would determine vertical shift. So now, how is this graph going to move? Well, we can describe it. Okay, so we're going to take the parent function. We're going to take y equals the square root of x. We're going to shift it, and we're going to shift it to, now this is x minus h shifting to the right, but this is x plus 3. Now, if you remember the trick, minus h goes to the right, plus h goes to the left. This means we're going to shift 3 units to the left. Okay, so we're going to shift left 3 units. That's important. Okay, so we're going to take the parent function and we're going to shift it left 3 units. That's crazy, right? But we proved it already. So we're going to shift to left 3 units, and then we will shift it up 2 units. Okay, so that's the description of the translation. We have the parent function. This is plus 3, so we're going to the left 3 units, and that says plus 2, the k, we're going up 2 units. And now we're ready to graph. So we sketch our graph, and then we'll see what is going on. Some fun stuff. I think this is neat, anyway. I mean, how cool is it that you can graph these things so easily without using any technology, just your brain? Now, we have our parent function again. This is parent, y equals square root of x. But we're going to shift that graph left 3 and up 2. So we're going to have the 0 point here, and we're going to go left 3, up 2. That's where the graph is going to start. And then everything else will be going with it. Boop. And that is what the graph will look like. So we have our parent function in the middle. The new graph is shifting left 3 and then up 2. So now we have the graph done. What will the domain for this be? Now again, we have domain, which is left to right. Pardon the noise there. So the domain will be from left to right. How far to the left does this graph go? The graph goes as far left as -3 because of that shift. So the domain is actually going from -3 out to infinity. And then what would the range be? How low does it go? How high does it go? So the range goes as low as 2. It'll only go as low as 2, right? Because we're shifting up 2. So the range then will be going as low as 2 up to positive infinity. That is our domain. That is our range. Okay, so we can state domain, we can state range, we can state all this stuff just by looking at the graph. And also the math makes sense. So there's no way we can take the square root of a negative number. So x cannot be anything lower than -3. So bam, right? It can be -3. All that stuff makes sense when you're looking at the equation as well. So we've described it. We've graphed it, we've got the domain, we've got the range, all this stuff on translation. So much fun. And now for the last one. Right? If we look at the last one, we can see that this is going to make a whole lot more sense now that we are doing much better. So the last one, f of x equals negative x plus 2 squared plus 3. What do you think the parent function would be? Okay, so the parent function is going to be y equals x squared, right? Because that's x to the second power. So we have the parent function, and we know what that's going to look like. That is the quadratic equation that makes our parabola. Boop. But we're going to do something to it. Okay, so we have to know how translations work for quadratics. We have y equals a, and then x minus h squared plus k. And again, a determines whether or not it's going to open up or down. Okay, will it look like this? Will it look like this? Will it be skinny? Will it be fat? H determines horizontal shift, where minus h is to the right, plus h is to the left, and then plus k is our vertical shift. And so we can tell all this information just from this equation. So what we can do now is describe the translation. We can take y equals x squared. Since we have the negative out there, it's actually reflected over the x-axis. Or again, I can take opening down. It's reflecting over the x-axis or opening down. If we have x plus 2, which means it's shifting to the left 2 units. That's important, an important distinction. So it's shifting left 2 units. That's the impact of the h. And then what about the k? That's going plus 3, so it's shifting up 3 units. How much fun is this? Too much fun. So we have our translations. We have described the translation. Now we can easily graph this without any technology other than what is between our ears. Okay? Do you need a calculator? No, I don't think so. Just need a little bit of thinking. Just a little bit of thinking, learning, and understanding. So remember, we have our original parent function, right? The parabola that looks like this. That's y equals x squared. But now what we're going to do is we're going to open it down now, and we're going to shift it left 2 units and up 3 units. How fun is that? So the original starting point, the vertex, and we'll learn about that later, is at 0, 0. But now that vertex is going to shift left 2 and up 3. That's the vertex. And instead of opening up, it's going to open down now. Okay, so it went left 2, up 3. That means it's going to open down this way. Pew! Very similar to the parent function, but the graph being upside down. As you can see, my handwriting, I'm hand drawing stuff, so it doesn't matter. So we have all these neat things that are happening just from translations. And finally, domain and range, and then we'll be done. Full understanding, right? How cool is that? So domain all the way to the left and all the way to the right. This graph will continue moving on to the left and to the right. So the domain is from negative infinity to positive infinity. And then the range, how far up, how far down. It's going to go as low as possible. It's never going to end. And how high will it go? It's going to only go up to 3. We said shift up 3 units. It's only going to go as high as 3 units. So the range is going to go from negative infinity, because it's going to keep going down, all the way as high as positive 3. And that is our range, because you got to remember interval notation, etc., etc. And that's not going away. So if you're looking at this going, oh, not interval, it's not going away. So get used to it. How do you read it? From negative infinity to positive infinity, from negative infinity to 3. That's how you read it. Get used to it. It's not leaving. So this stuff is fun. You can graph all these complicated things without using anything other than a piece of paper, a pen, and the computer in between your ears. And I'm out.